Hi. If we observe the graph of a smooth function, that is a function with a tangent at every point, we cannot fail to notice that in correspondence with the maximum and minimum points of the function within the domain of definition, the tangent is horizontal. Knowing that the slope of the tangent is the number f prime of x, this says that minimum and maximum points must solve the equation f prime of x equals 0. One of the first to note this observation was Fermat in 1638, about 50 years before Newton introduced differential calculus. Fermat expressed this condition, describing it in words as follows. So you should start calculating f of x plus h, then you subtract f of x and divide by h. So far, you computed this ratio. Now, since Fermat was working with polynomials, this quantity will be a polynomial in h, so something like this. Now, Fermat says, assuming that h is small, we can neglect this part containing the powers of h. So basically, he is doing the limit for h going to 0, but he had not this operation defined yet at that time. And the limit when h goes to 0 is this number a that turns out to be the derivative. And finally, he says you should solve for a equals 0 to find the minimum maximum points. Now, what is precise about all this? Is it true that the extremal points coincide with the solutions of the equation f prime of x equals 0? The answers to these questions are the objective of this video. First of all, we notice that the tangent is horizontal even at points that are not global minimum or maximum points. If the graph of the function were the profile of a mountain, the tangent would be horizontal not only at highest peak or deepest valleys, but also at the smaller summits or secondary valleys. This leads to the definition of local extremum. A point x star, like this one, is, for example, local minimum if it is a minimum, but for a small part of the domain. So let's say in a neighborhood of the point x star. Formally, we say that given a function f of x, x star is a local minimum or relative minimum point if there exists a neighborhood of the point such that the function there has a minimum, and this is expressed by this. Similarly, local maximum are defined. It is clear that a global minimum or maximum are also local, but not necessarily the vice versa. A second observation is that the property of a horizontal tangent at extremal points generally holds if these are internal to the interval. For example, let's take the function f of x equal x on the interval 0, 1 with the endpoints included. So it is clear that this function achieves the minimum at x equals 0 and the maximum at x equals 1. However, the derivative is constantly equal to 1, so it is never equal to 0. So these 2 points do not verify the equation f prime equals 0, which has no solutions, by the way. All right, so we are ready now to state a proper theorem, which is named the Fermat theorem in honor of Fermat, who discovered first this condition. Let's say, suppose we have a nice function, so differentiable function, a point x star, which is an interior local extrema. For example, here we write for a local minimum. There exists a neighborhood entirely contained into the domain where the function has a minimum there. Then, at that point, the derivative of the function must be equal to 0. Now, the proof of this is easy because we can see with a figure. Imagine this is the situation. We have a minimum at point x star. We pick a second point, x star plus h, here at right, so with h positive, and we compute the incremental ratio to compute the derivative. So we start doing f of x star plus h minus fx star, which is positive because this point is a minimum, so this value is bigger than this one, so the difference is positive, divided by h. which is positive here because h is such that the point x star plus h is at right. So we have positive quantities. When we send h to 0, we get the derivative, and because of the permanence of sign, this remains positive. If we repeat the argument, by taking a point now x star plus h at left of x star, so with h negative, we still have that f of x star plus h is larger than f of x star because x star is the minimum value for f in this neighborhood. But when we divide by h, we are now dividing by a negative number, so this fraction will be negative. So when we send h to 0, we get derivative of f at point x star negative. Combining the two, this must be possible if and only if f prime of x is equal to 0. Fermat's theorem highlights the equation f prime x equals 0 as a method to determine minimum maximum points for the function. But how decisive is this equation in determining the extrema of f? We already said that if the extrema are not internal, the derivative might not even be 0. Furthermore, the derivative might be 0 and the point not be an extremum. An example of this phenomenon is provided by the function f of x equal x cubed. Now this function, because of properties of powers, is strictly increasing. So in particular, this means that there are no minimum maximum points for this function, because you can always increase or decrease the value. However, if we compute the derivative, we realize that at 0 the derivative is equal to 0. So x equals 0 is a point where the tangent is horizontal, but cannot be a minimum or maximum point. Now, because of these, points where the derivative is equal to 0 are called stationary points. So we give them a special name because they could not be necessarily a minimum or maximum point. Finally, we also note that a point can very well be an extremum, but the function, if the function is not differentiable at point, the derivative could not capture the point in question. For example, if you look at the function f of x equal modulus of x, this function clearly has a global minimum at x equals 0. However, there is not the derivative of f at point x equals 0, so if you would write the equation f prime of x equals 0, you would never find the point x equals 0. In conclusion, despite having many limitations and exceptions, the equation f prime of x equals 0 is still important in the search of extrema. If, for example, the domain is an open interval and the function is differentiable on the interval, then the extrema must necessarily solve the equation f prime of x equals 0, which is also called the first order condition. So solving the first order condition means, in this case, determining the possible extremum candidates, which can be, in many optimization problems, a first step toward a solution. Well, now it's your turn. And to better understand how Fermat's theorem works, you can, for example, determine the stationary points of these functions and try to classify them, understanding if they are minimum maximum points, using only Fermat and eventually the Weierstrass theorem. Or you could work at a little bit more abstract level with this very simple problem. Good job!